So, having looked at the definitions, I can talk in terms of some formulae, simple formulae. Now, supposing I have a point source like this emitting I, right, and I want to find out what is the illumination here. Let us say the surface area is ds, small surface area is ds, and if I want to find out how much flux coming here, I must find out what is the solid angle subtended by ds onto this point source, right, because I into solid angle will give me the flux that is coming out. I want to find out the illumination here. Now, when I want to find out the solid angle, I must take the projected area normal to this direction, right, projected area normal to this direction. So, if this angle of incidence is theta, this angle also will be equals to theta. So, if this area is ds, the projected area will be ds cos theta, projected area will be ds cos theta and divided by r square, that is d omega. The d omega is the solid angle subtended at this point by this surface ds, right. So, ds cos theta, because projected surface area is ds cos divided by r square, that is d omega. So, the flux will be I into d omega, which will be equals to I ds cos theta by r square. So, that is the flux received here onto this surface. And what is illumination? This flux divided by area of the surface, that is ds again. So, illumination is f by ds again. So, this ds and ds will cancel out. So, I cos theta by r square, that is inverse square law, that is inverse square law. So, illumination received on this surface is I cos theta by r square. So, if I have a point source at a distance r, angle of incidence is theta, then the illumination will be I cos theta by r square, I cos theta by r square, right, I cos theta. All right. So, this is what it is. So, like this is shown again, one candela is the source, the distance is r. So, total in all direction, if it is a one candela source, it will emit 4 pi I 4 pi flux in all direction divided by 4 pi r square will lead to I by r square. So, it is all on normal direction, if it is along normal direction, but if it is general equation will be, because there will be general law would be if it is projected. So, if it is spherical front going in all direction, that is simply I by r square, because theta would be equals to 0, cos theta is equals to 0, right. So, normal incidence. So, for a receiver at a distance, say this is my source, this is normal direction. So, I cos theta by r square, I cos theta, because this is the theta. So, I cos theta by r square, that is what it is, this was theta. So, I cos theta by r square. Now, cos theta can be written as h by r, and therefore, height if you know I h by r cube. So, that means it is a simple thing, that hardly anything in this. If I have a source, I want to find out what is the illumination there, height is known and its distance r is known, then it is simply I h by r cube, a simple extrapolation of that earlier relationship. So, that is how one can relate illumination with intensity, right. So, or you can write in terms of I cos cube by h square, etc., all kind of permutation combination you can do, because this is cos theta is nothing but h by r. So, therefore, you can write just change this I h by r cube, make it h cube, or cos cube, actually you have to divide then by h square. So, that is how it is. All right. Now, Lambert's law states, this is inverse square law and this is quite often we use them. Lambert's law states that if its intensity along given direction of a flat source its normal direction is I 0, intensity along any other direction will be I 0 cos theta. The intensity, for example, I have a source like this, right, all lamps are vertically downward, that direction is I 0, but if I put now my flat projected surface at an angle, the intensity there would be I 0 cos theta. So, intensity along other direction for sources could be I 0 cos theta. We do not use this much, but anyway, since there is a law, I am just stating this. Intensity of uniformly diffusing plane surface varies as given, I 0 is in the normal direction, right. So, intensity varies along different direction. Okay. Now, this principle is important. This is called principle of integrating sphere. Supposing I have a sphere and I have a light coming in from some point, through one point light is entering there. Now, what will happen if this surface is diffusing, then it will reflect in all directions. So, I will have again infinite reflection. Now, at this point what will happen? I will have very high brightness, right, but I will have illumination on the whole surface as well, even though direct light is not being received on those places. That is because of the infinite number of reflections coming from this place. After first reflection, whatever enters into the diffused field, that will have infinite number of reflections, right. So, infinite reflection of entering flux F after first reflection. So, Fr is the first reflected flux, if R is the reflectivity of the surface, 1 minus R is the fraction that is absorbed, R is the fraction that is reflected. So, after first reflection, Fr is the flux that will enter into the space and it will have infinite reflections. So, Fr square will be what will be available after second reflection, and then after there are all interreflected flux will be first reflection, second, third, fourth, etc., infinite number of them. It is in a GP series. First one is Fr. So, Fr, R is the reflectivity, so 1 minus R. So, R is the average reflectivity or constant reflectivity of that sphere. So, this is the total reflected interreflected flux. I am leaving the first one, F I am leaving, but Fr is what enter, and this goes on reflecting several of them after second, third reflection. So, general brightness will be more or less uniform, even if the brightness here is a point, but you will find an uniform brightness all across the internal surface because of that many number of interreflected component, number of such reflection, and this is the total flux. And what will be the illumination due to this? Illumination will be simply Fr 1 minus R divided by internal surface area, which could be some pi r square, or let me say internal surface area of the sphere, spherical one, internal surface. So, illumination will be given by this. So, illumination will be due to the reflected component, only due to reflected component the illumination, general illumination, it will be there in all surfaces, like the top surface, the bottom surface, side and everywhere. So, all internal sphere surfaces, its illumination will be given by, this is the total reflected flux, interreflected flux divided by the internal surface area of this. So, this is called principle of integrating sphere. Now, a room can be also treated like this. Supposing I have got one small entry point, I put off all light, one small entry point through which light is coming, or a window, let us say. Now, window will have a direct light coming somewhere, but you will have lot of reflected component. So, general bright illumination would be there in all the surfaces, and that will be given by this kind of a formula. We will use this sometime later on. We will use this sometime later on when you try to calculate out the total illumination on a surface. All right. So, this is called principle of integrating sphere. The point that I am trying to make is that light does not come from, the direct light is one thing, but there is something called a diffused light also, which will come from reflected component, right. So, illumination that you receive on your table, reading table, not only comes from the direct light, but it also comes from the wall and those places as well. And when I want to estimate that, I can use this formula, right. Total light that is received on a working plane or a task plane or the object that you want to read, let us say the blackboard, there it comes directly if there is a lamp coming in, if there is a lamp or window through which the sunlight comes, but there will be a total reflected component also which will illuminate that portion, but all other portions as well. So, that is there we will use this principle. Okay. So, let us proceed. Now, supposing I have a point source, then we have seen that I depends upon 1 by r square, E is proportional to 1 by r square, illumination. Now, supposing I have a tube lamp like sound we talked about, and I know the I per unit length or flux per unit length, I will call it. It will pass through twice pi r into 1. If I have a lamp, long lamp, and its flux per unit length is known to me, so at any distance r from there, it will be f divided by twice pi r. I have a long source, f per unit length. So, at a distance r, it will be uniform illumination in a cylindrical internal surface, and it will be f divided by twice pi r, right, because twice pi r is the surface area into 1, and this was per unit length. So, through 1 length. So, therefore, f. So, from line source it is proportional to 1 by r. For point source it was proportional to 1 by r square. Now, if I have an infinite source, let us see how it works, and that has got a relevance, because my sky is something like this, sky volt is something like this, it is a hemispherical sky volt. Therefore, if I am interested unobstructed illumination on anywhere on the ground surface, I might be interested from an infinitely large source, sky volt, sky. Supposing I have a ground field, open field, and sun is all covered by cloud, ideal condition. On a cloudy day you see uniformly bright sky, diffuse sky, you do not see the sunshine. So, let us consider that sort of a situation. Actual skies are not like that. So, I have a totally covered sky, let us say, and just this infinitely large source at an infinite distance, right, at an infinite distance, and I am interested in finding out the illumination here. So, this illumination I can find out by considering a small surface area here, like I have done earlier, small surface area. So, this is a small surface area in the sky, and this is the surface on which I want to find out the illumination. This is the surface on which I want to find out the illumination. So, this is the center of this circular, I will say it is a ring. It is not unlike there we took a volume element. Remember, in sound we took a volume element for diffuse scenario. We said that everywhere the field intensity will be same, therefore, I pick up a volume element, and which will pass on sound to a surface here. But here I am sky volt, so which is a surface actually. So, it will appear like a surface, in between I am not bothered, the surface, that surface is acting like a source. The sky volt acts like a source, and this is the distance of this one, this is the this distance is r, and it is a surface, this distance is this distance is, if this distance is r and this angle is theta. So, this distance is how much? R sin theta. I am interested in finding out the surface area of this one. So, it will be r sin theta d psi. Psi is the angle along azimuthal direction, this one, this angle it makes here is this, and vertical this height will be how much? R d theta, because this is the angle, you know, the theta angle is this angle, theta angle is this angle, theta angle is this angle, this is the surface I am looking at. So, this is r d theta, right, elevation angle changing by theta, because this circle could have been somewhere there. So, r d theta. So, this length of this one is r d theta, because r is the distance, the elevational change is theta at theta angle d theta. So, I have taken this as theta angle, and there is a change in the elevation as r d theta. So, this r d theta is the height, and r sin theta d phi is the width of a surface there, small elemental surface there, which I call as ds. And if its brightness, let us say, is uniform brightness is B, sometime brightness is denoted by B, sometime it is denoted by L, like she said luminance. So, luminance sometimes therefore people denote by L, and brightness sometimes we denote by B. I might use them interchangeably. Some book you will find it is written as B, somewhere L. So, might use, most probably I will use most of the time B, brightness as B. So, for uniform brightness B, the intensity of this from this surface will be equals to d I is equals to B into ds. Let us say sky is uniformly bright, you know, uniformly bright, then B into ds will be the intensity, because brightness is defined as candela per meter square. So, B candela per meter square multiplied by ds, that is the source, and B ds therefore will be equals to B r square sin theta d theta d phi, right. So, what will be the illumination here? I by r square cos theta, I by r square cos theta. So, illumination d E will be given as B r square sin theta d phi cos theta divided by r square, if r is this distance. Now, you see what is happening, this gets cancelled. So, therefore, it is independent of r, independent of distance. For a point source, it is inversely proportional to r square. For a line source, if I define the flux as flux per unit length, it is inversely proportional to r. For a large source at infinite distance, it is independent of r. So, 1 by r square, 1 by r, or it is independent of that. So, this is independent of that. So, d is independent of that, and here I want to find out illumination, then I will integrate this, I will simply r square will cancel out, I will from whole of this chi volt, if I want to find out the illumination on this surface, it will be given as integration of this one, and theta will go from where to where? Theta will go from 0 to 2 pi, and phi will go from, theta will go from 0 to pi by 2, and phi will go from 0 to 2 pi. And since this is nothing else is depending on 2 pi, so I can take out, I can write like this, you know, I can simply write, this is what I can write, and this will come out very easily. So, theta phi varies from 0 to 2 pi, theta varies from 0 to pi by 2, and you remember this sin theta cos theta d theta, I wanted to do the integration which we did earlier also. So, this is simply sin theta 2 theta by 2, which if I integrate, I get cos 2 theta by 2 into 2 minus sin, and then put this 0 to 2 pi. So, this is simply, first one is pi by 2 corresponds to pi cos pi, and there is a minus sign. So, minus sign outside, minus cos 0, so it is half. This you remember this was half, we did it earlier also, I believe something similar. So, this is half. So, this integration is half. So, I am left with now what I am left with the 2 pi, this from this I get 2 pi, because this varies from 0 to 2 pi, and this simply half b, so pi b. So, for a uniformly bright hemisphere, the illumination E on horizontal surface is given as simply pi into b, for uniform brightness, and is independent of the distance. So, something like a large hemisphere, here I get illumination as simply pi into b, pi into b, pi into b, all right, pi into b. Okay. So, this is important deduction, we will require this, we will require this. So, the illumination from an infinitely large source is independent of distance, and sky can be treated something like this as a source, right. But then sky brightness is not uniform, right, sky brightness is not uniform. Uniform brightness only you can get if it is sun is fully covered, because sun is too large. So, if this is my this is my this is my earth, the sun's radiation comes from all direction. So, it will come from the sky volt, diffused light will come from sky volt if the sun is blocked. We had diffused radiation, you remember, we had diffused radiation and direct radiation. So, if sun is blocked, then you can have uniform brightness, but otherwise the sun is there. So, uniform brightness is an ideal situation, it really does not occur. Initially it was thought that perhaps for the overcast sky, fully overcast sky is uniform, right, but such kind of sky really does not exist in reality. So, brightness of the sky can vary instead of being constant. So, it actually varies, and if you remember when we talked of climates, we said that the brightness near the horizon in tropical countries is much higher, it is high, very high, right, it is very high. So, we will look into this. So, it will vary, and therefore, we got to take the specific sky for specific, maybe specific location. The type of sky that would be say suitable for, let us say, subtropical areas is not suitable for tropical areas. It also depends upon, might depend upon the pollution level and things like that, many other things, because how much radiation is coming finally, this will all depend upon. So, brightness of the sky can vary, and therefore, when you want to calculate out, you can calculate out, right. We will do that sometime later on, but let us look into some more fundamentals, like you were talking about color. So, a scale of color is called Munsell scale. Scale of color is called Munsell scale, right. Now, this scale actually color depends on three things. Color depends on three things. It depends on reflectivity as well, because if it is not reflecting, it will appear as black, and if it is highly reflecting, it will appear as absolutely white and reflecting all wavelength. But if it reflects selectively, then also, supposing it is only reflecting green color, let us say particular wavelength corresponding to the green color, if reflectivity is 0, then it will also appear black. So, the shades of the green will depend upon reflectivity. So, it depends upon reflectivity, also brightness. So, therefore, this scale has been actually devised called Munsell scale. We may not use this much, but at least I want to introduce this to you, because task illumination really does not require this much, but you can have always question. So, that is why I thought I should talk about this. So, you see there is a scale along this line, vertical line, it is black to white, black to white, black to white. Black is 1, white is like it is 1 to 10 scale, 9 scale actually. So, these are called value, these are called values, right, values. So, value varies from 1 to 9, relative scale, relative scale. Actually, value corresponds to reflectivity, value corresponds to reflectivity. Then there is hue scale, hue scale along this direction, right. So, for example, you have red, which corresponds to something, some value of red, yellow, green, blue, etc., etc. So, there is a hue. Hue is associated with the wavelength. You talk about hues in literature also, sometimes people do talk about. So, hue is this, right, hue, value, and there is a chroma scale. Chroma scale in this direction, hue scale is in this direction, chroma scale is in this direction. Chroma scale is related to kind of a brightness. These are all relative scale. So, let us see something more. So, chroma can go from very bright, it depend upon brightness. For example, red color can be bright red or less bright red, and there can be reflectivity. So, you define this color defines in 3 terms, like how it is written. Let us see if it is written like this. So, principal hues are red, yellow, green, blue, purple, and intermediate hues are, that is what I said, the circular scale, red, yellow, green, etc., etc., and intermediate one are yellow, red, etc., etc., right. So, these are the hues: yellow, red, green, yellow, blue, green, purple, blue, red, purple, etc., etc. Hue, concept of color, the wavelength, as I mentioned, that is, it depends upon the wavelength, of the light itself. Concept of color. Value is related to reflectance, that is what I said, value. So, it is high value means it is white, low value means it is black. One value would be lowest would be black, highest will be 1. It is in relative scale. And then chroma is brightness. Brightness, like it is more of subjectively dealing with the situation also. Bright red, dull red, you talk of this kind of thing. So, when one is expressing color, one will write it like this: 5 red, 5 R, 5 R 4 by 10. What it means is hue is 5, right? Hue is 5, reflectivity is, relative reflectivity is 4, and chroma brightness is 10. So, let us go back to 5 R 4 by 10, 5 R, this will be written the color. If in detailed color you are interested in, right. So, color if you are interested in. So, 5 R, right, 5 R, right. So, R is in this direction, R, 5 R. So, hue scale is 5 R, right, 5 R. 5 was what? 5 was it value? Hue here, yeah, hue 5 R. 5 R is somewhere there. Chroma is 10, so it is somewhere there. The brightness is 10, so it is somewhere here actually, and value was how much? 4 by 10. 4 is somewhere there. So, it is not very bright, I mean it is not, reflectivity is not very high. So, it is expressed in this kind of scale actually. Red of hue 5, that means not going towards yellow red or is average red actually. And then value 4 means reflectivity is not so high, 5 would have been average. Chroma means relatively bright, 10, 18 it can go up to 18. So, these are used in what you call decorative lighting. Task illumination, we are not really interested in this, but largely, but this is the scale. So, that distinguishes all. So, color is not as understood simply through wavelength, it is understood through wavelength, reflectivity, as well as relative brightness we distinguish, right. We may not use this anymore in our class anymore, because we are not dealing with decorative lighting, we are dealing with illumination related to object lighting and task lighting for purpose of reading or similar kind of activities, human activities. So, that is what it is. You can express the color in this manner, right. All right. Now, reflection, as I was saying, is important, reflection is important. This is polished surface, that is specular reflection. This is matte surface, fully diffuse, but I can have partially diffuse also. And this is diffuse and spread, this is diffuse and specular. So, this is also spreaded somewhere. So, generally task illumination, this one would be that what we will consider, like while defining apostille we actually consider this sort of situation, or integrating sphere is considered this sort of situation.